So far, in this course, we have always visualized the simplex method as an algorithm that moves from one basic feasible solution to the next by going along edges of the polyhedron. In this video, we will see a completely different way of visualizing the simplex method. In particular, this new visualization will allow us to understand why this method is called the simplex method. To do this, we consider a linear programming problem in a very special form that we have never seen before. This form is very similar to the standard form. In fact, we're minimizing C transpose X, we have constraints of the form AX equal to B, and then we have non-negativity on all the variables. The unique difference is that here we have one more constraint, which is sum of all the variables equal to 1. This constraint is called the convexity constraint. Of course, this is a very special linear programming problem. However, it can be shown that every linear programming problem can be brought into this form as long as it has a bounded feasible region. And you can find more details in exercise 3.28 of the textbook. So let's focus on our new linear programming problem, which I have rewritten here at the beginning of the slide. And now I want to write the same problem in a slightly different way. I introduce a new variable that I call z and that I set to be equal to C transposed x. So at this point we can substitute C transpose x with z in the objective function, and we have the new constraint sum of the ci xi equal to z. So clearly the two linear programming problems here are equivalent. The reason I have written in the problem below all the equality constraints together, except for the convexity constraint, is that very soon I'm gonna make use of these vectors AI, CI. So let's see how we can visualize these vectors. In my space, the horizontal plane will be an m-dimensional space that contains the column of A. My picture here is of dimension 3, and my horizontal plane is the one over here that in fact contains my points A1, A2, A3, and A4. So in the picture in this example here, I have m equal to 2. In this picture, I also have a vertical axis. This corresponds to a one-dimensional space that is associated with the cost components Ci. So while in the horizontal plane I can draw A1, in the full space I can draw A1, C1. And of course the same thing happens for all the other AI, Ci, for I that goes from 1 to n. In our linear programming problem, our objective is to construct a vector bz, which is a convex combination of the vectors ai, ci, such that z is as small as possible. We have now understood how to visualize all the points ai, ci, and what about the vector bz? Well, z is a variable, so we're gonna visualize instead all the points of the form bz for any z. These points lie on a vertical line, which is called the requirement line. The intersection of this line with the horizontal plane is exactly the vector b. At this point, we can easily visualize when our problem is feasible or infeasible. In fact, if the requirement line does not intersect the convex hull of the points AI, CI, then there is no way of obtaining B as a convex combination of the AIs. Therefore, the problem is infeasible. On the other hand, if the requirement line intersects the convex hull of the points AI, CI, then the problem is feasible, and an optimal solution will correspond to the lowest point in the intersection. We have already discussed several concepts, so let's immediately see an example. In this picture, we have again m equal to 2, because this is a three-dimensional space, and we have n equal to 5, and the 5 points AI, CI are B, F, E, D, and C. The vector B is over here, so this is the requirement line. Now the convex hull of my 5 points AI, CI is the polytope drawn in the picture, and clearly the requirement line intersects it. This immediately implies that the problem is feasible. An optimal solution corresponds to the lowest point in this intersection, which is the point G. From the picture, we can also tell the optimal cost because this is the third component of the vector g. In other words, it is its height. To proceed further with our geometric interpretation, I need to define a simplex. And to do that, I need to define what it means for a bunch of vectors to be affinely independent. So let's see these definitions. A bunch of vectors that we call y1, y2 until yk plus 1 are said to be affinely independent if these other k plus 1 vectors are linearly independent. And these new k plus 1 vectors are simply defined as y1 minus yk plus 1, y2 minus yk plus 1, yk minus yk plus 1. So essentially we're picking one of the original vectors and removing it from all the other ones. Now we can finally define a simplex. A k-dimensional simplex is the convex hull of k plus 1 affinely independent vectors in Rn. For example, let's now consider 3 points. There are only two options. Either they are contained in one line, so they are collinear, or they are affinely independent. If they are affinely independent, they determine a two-dimensional simplex. This is the triangle obtained as their convex hull. What if we have 4 points? Also here there are only two cases. They either lie on the same plane or they are affinely independent. If they are affinely independent, then they determine a three-dimensional simplex, which is the pyramid obtained as the convex hull of these 4 points. Now that we know what is a simplex, we can give a geometric interpretation of basic feasible solutions. Remember that in our original problem we have m plus 1 equality constraints. This is because we have m equality constraints plus the one equality constraints that is the convexity constraint. By definition of a basic feasible solution, such a solution is associated with a collection of m plus 1 linearly independent columns of the constraint matrix. These columns will be of the form ai, 1. And again, the 1 comes from the convexity constraint. Every column ai is associated with the point aici in our picture. So a basic feasible solution is associated with m plus 1 of these points aici. This will be called the basic points. Of course, the remaining points aici will be called the non-basic points. In our example here, a possible choice of basic points is C, D, F. You can now show that these m plus 1 basic points are affinely independent. And this implies that their convex hull is an m-dimensional simplex, which we call the basic simplex. Again, if our basic points are C, D, F, then the basic simplex is the shaded triangle here with vertices C, D, F. Now let's assume that the requirement line intersects the m-dimensional basic simplex. The intersection will be, of course, of the form bz for some z. This means that this intersection vector bz can be written as a convex combination of the vectors ai, ci. Then the current basic feasible solution corresponds to the weights xi's used in expressing bz as a convex combination of the basic points. The cost of such a basic feasible solution will be exactly z. In the picture here, we have that our basic simplex CDF intersects the requirement line in the vector age. So age corresponds to the basic feasible solution associated with these basic points. Now the height of age represents the cost of the solution. Now we've understood basic feasible solutions. So let's now talk about change of basis. In a change of basis, we have that the new point AJCJ becomes basic and one of the current basic points becomes non-basic. Let's again look at our example to understand a little bit better the situation. Let's say that our current basic points are C, D, F. And let's say that we want B to replace F in the basis. So the new basic simplex will be the convex hull of B, C, and D. So this triangle over here. The new basic feasible solution is the intersection of this triangle with the requirement line, so it is the point I. Another possibility, starting again from the basic simplex CDF, is to make instead the point E basic, replacing, for example, the point C. The new basic simplex is now the convex hull of DEF, so it's the triangle over here. The corresponding basic feasible solution is the point G. Now, how can we understand if a basic feasible solution is better than another one? Everything we have to look at is where is the basic feasible solution in our requirement line. In fact, we know that the height of the basic feasible solution represents its cost, and we want to minimize such a cost, so lower is better. In this case, G is better than H, which is better than I. A nice way to understand if a basic feasible solution is better than another one is to look at the dual plane. This is the plane that passes through the basic points. Once again, if our basic points are C, D, F, then the dual plane is the unique plane that contains the shaded triangle. Now, after a change of basis, the cost decreases if and only if the new basic point which enters the basis is below the dual plane. For example, the point E is below the dual plane, therefore the cost will decrease. On the other hand, the vector B is above the dual plane, and so the cost will instead increase. Therefore, the dual plane gives us an information that is similar to that given to us by the reduced costs. Namely, the reduced cost is negative if and only if the new point is below the dual plane. It's interesting to see that there's a stronger connection actually between the reduced cost and the dual plane. In fact, you can show that the reduced cost of a variable xj is exactly equal to the vertical distance from the point AJ-CJ to the dual plane. For example, let's say once again that CDF is our basic simplex and that we're considering having B enter the basis. Then the reduced cost is the distance from B to the point in the dual plane obtained by going downwards from B until you intersect the dual plane. If the new point is below the plane, then the reduced cost is the negative of this distance. So once again, requiring the new basic point to be below the dual plane is equivalent to requiring the entering column to have negative reduced cost. So now we have a clearer idea about the point that should enter the basis. What about the point that should exit the basis? Once you have decided which point enters the basis, then every exiting point leads you to a different basic simplex. Now we can look at the union of all these m basic simplices together with the original basic simplex, which is the one that we had before the change of basis. We obtain the boundary of an m+1 dimensional simplex. Let's immediately visualize this in our example. Once again, before the change of basis, our basic points were C, D, F. And let's say we have decided to have E enter the basis, which really is the only thing that makes sense because it is the only point not in the basis which is below the dual plane. Now, depending on who will leave the basis among C, D, and F, we obtain three two-dimensional simplices. If C leaves the basis, then the simplex will be DFE. If F leaves the basis, the simplex will be CDE. And if instead the D will leave the basis, we will have the simplex CFE, which is in the back of this picture. So we have three new two-dimensional simplices and the old two-dimensional simplex. Their union is the boundary of the three-dimensional simplex, which is the pyramid with vertices C, D, F, E. So why is it so important to look at this m+1 dimensional simplex? This is because our requirement line intersects this m+1 dimensional simplex. In fact, we know that it exits this simplex through its top face, which is the m-dimensional simplex corresponding to the basis before the change of basis. Therefore, the requirement line should also enter this m+1 dimensional simplex through another face. This face is one of the m-dimensional simplices that can be obtained after the change of basis. So we should choose the exiting variable in order to obtain exactly that m-dimensional simplex. Let's again look closely at our example. Our requirement line exits our pyramid through our top face with vertices C, D, F, and it enters the pyramid through the face with vertices D, E, F. So DEF is the new basic simplex, and so C should exit the basis. Of course, the reason we're doing the change of basis in this way is that if we chose instead an m-dimensional simplex that doesn't intersect the requirement line, then we would have obtained a basic solution that is not feasible. Now we know everything about pivoting, and we can even visualize it with a physical analogy. Let's again think about our original basic simplex with vertices C, D, F. And let's think of this simplex as a solid object which is anchored at its vertices C, D, and F. Now we want to remove C from the basis and have E enter the basis instead. So we can imagine that we're grasping the corner C of the basic simplex and we're pulling it down until we reach E. In this way, from the old simplex, we obtain the new one. While doing this, our basic simplex will pivot on the edge FD as if it was anchored there. And this is where the word pivot that we use in the simplex method comes from. Of course, we've also understood where the word simplex comes from, because essentially everything we discussed about this geometric visualization is based on simplices. Let's see now another example where we perform more than one pivot. To obtain an understandable picture, we need to have at this point m equal to 1. So our picture loses one dimension as opposed to the previous examples. The points from 1 to 8 in the picture are my points AI, CI. So in particular, it means that I have n equal to 8. In this lower dimensional case, our simplices will be one-dimensional. And let's say that our initial basis has the variables 3 and 6 in the basis. So our initial basic simplex is the segment 3, 6. We're going to use the pivoting rule that chooses the variable with the smallest possible reduced cost. We've seen that geometrically this means that we choose a point AICI to become basic if it is below the dual plane and with vertical distance from the dual plane that is the largest. So now from our initial basis we need to compute all these vertical distances. For example, for the point 2, we should compute the distance from this point to the point above it that lies on the segment 3, 6. Similarly, for the point 4, we should calculate the distance from the point 4 to the point above it on the line obtained by extending the segment 3, 6. If you calculate all these distances, you will see that the one with the largest distance is the point 5. So now 5 enters the basis and we have to decide if 3 or 6 leaves the basis. To do so, we construct the segment 6, 5 and 3, 5. The one that intersects the requirement line is 3, 5, so we have 6 leave the basis. For the next pivot, we only have the points 4 and 8 below the line connecting 3 and 5. The one with the largest vertical distance to such a line is the point 8. So we have 8 enter the basis. Again, we form the segment 3, 8 and 8, 5. The one that intersects the requirement line is 8, 5, so we will have 3 leave the basis. The new basic simplex is then 5, 8, and you can check that it is optimal. And this concludes our video on the column geometry of the simplex method.